Physics 2 is different than Physics 1 because in Physics 1 we often talk about the macroscopic and look at the motion of things, motion of planets, how objects move under the conservation of kinetic and potential energies. But it's also, things that you can see and visualize. In Physics 2, it's all about the atomic and microscopic. But it's also really, really important in terms of humanity in the 21st century. And here's the essential problem when we look at this beginning slide, is that we have a picture of the new, or at least the semi-new, and the old. But they both involve the white stuff that's coming out, which is steam. And so for 2 centuries now, the acceleration of humanity has been fueled by burning things. And that's a big problem. So it's sort of highlighted in a couple of quiz questions in chapter 14. One of the points, one of the big takeaways is that our reliance on fossil fuels and in burning stuff is because of a high energy density. And that's our big challenge, is to figure out how to live without accessing that high energy density. Because seriously, we've just been burning and burning stuff. And we have to figure out how to make it stop. So understanding thermodynamics is a really important step in trying to understand why we are so dependent on these energy density fuels, and then how we could potentially shift that dependency. So in this chapter, we're going to talk about the first law of thermodynamics, and then we're also going to talk about heat engines. So those are the two big pushes. This video is about the first law. And here it is. It looks pretty simple, right? Okay, so U represents internal energy. And we talked about this in the previous chapter, how the internal energy is represented by the kinetic energy, the average kinetic energy of molecules, especially in an ideal gas format, where there aren't really any intermolecular bonds. So that this internal energy, if it's kinetic, is going to have a direct correspondence to temperature. And so we can measure internal energy indirectly by measuring temperature. So changes in internal energy are also going to be accompanied by changes in temperature. Q is for heat, just like in chapter 14. Heat can enter a system or leave a system. And this concept about what a system is very important. So heat is how energy enters or leaves a system. And then W is for work. That's a physics 1 concept. So if we imagine that energy is in a closed system, if the system expands outward, it's doing work on the outside world. But if it's being compressed, that means work is being done on it. And that's how come the W is a negative sign, because if the work done by the gas is a positive number, it's expanding outward, then there is going to be a net energy loss for the system. It has given up energy to the outside world. And that's how come it's negative. And we'll talk a little bit more about that when I do a video lesson on problem solving with the first law. So PV diagrams are going to be really important. Looks a little bit like chemistry. But again, when we talk about what our system is, we want to think about a closed container. And then whatever is inside that closed container, that's our system. And so when we think about work done, when volume expands, when we see movement on the horizontal axis of a PV diagram, when we move from the left to the right, that volume expands, and that means that the system is doing work on the outside world, which is going to be an energy loss. So the work that goes into expanding is no longer available to our system. However, when we're compressed, when work is done on the system and the volume shrinks, if delta V is negative, then the work done is negative, and energy will be available to our system. The first law of thermodynamics involves three variables. So internal energy, heat, and work done. But in physics, we always are looking for ways to simplify a complex relationship. So the first law involves three variables, even though it looks kind of simple. But if all three variables are changing at the same time, it's kind of hard to predict the future. So what we do instead is we take a look at simplified versions of the first law. And the first simplification is an isothermal process. Now, isothermal means that the internal energy is not going to change. So any heat flow in or out is directly going to go into work done by the gas. Another simplification is the adiabatic process, and that's where there's no heat flow into or out of the system. If there's no heat flow, that means Q is equal to 0, and any work done by the gas is going to lead directly to a temperature change. You notice that they're both curves, and the reason why they're curves is because of the ideal gas law, pressure and volume being inversely related. So it's really hard to tell isotherms and adiabats apart from each other on a PV diagram, but they both have this inverse shape. And it depends on which direction you're going. So if there's an expansion, if delta V is bigger than 0, then that means there's going to be an overall loss of energy. And if it's isothermal, that means the change in temperature is 0, so the change in internal energy is 0. So any work done is going to directly lead to energy being heat being released or absorbed. And then two more important processes that simplify the first law. One is isobaric. And so in this case, work done, which is the area under the curve. But if the pressure doesn't change, then that area is the area of a rectangle. So the work done would be equal to the pressure times the change in volume. And if we have another process where the volume doesn't change, an isovolumetric one, then that means it's impossible for it to do work. There's no change in volume, so there's no work done. And so if that's the case, then the work done is just going to be pressure times the change in volume. Once again, if the change in volume is positive, then the work done is positive. If the change in volume is shrinking, it's negative, then the work done is going to be negative. Okay, so once again, pressure times volume. The SI units for pressure are going to be newtons per meter squared, and the SI units for volume are going to be meters cubed. So when you multiply those two together, you get the units for energy. So that's really a big component of the PV diagram, is that each location is going to, on the PV diagram, is going to correspond to a particular temperature. And a set of all points where the temperatures remain the same is called an isotherm. So here's some simplifications for the first law. Isothermal means T is constant, which means delta U is 0. So any heat is going to go strictly into work done. Isobaric means that the pressure doesn't change. And we have a couple of simplifications. So the work done is just going to be pressure times change in volume. And so the change in internal energy is just going to be related to the heat that's added minus work done. Isovolumetric means that no work can be done. So any heat flow is going to be equal to a change in internal energy, which sounds a lot like heat capacity, doesn't it? And finally, adiabatic means that Q is equal to 0. So I have a chart here, and I'm going to show you how to use that chart in the next video. This chart is designed to help you make good choices as you're solving problems that involve the first law. Okay, and of course, it applies to the human body as well, but we're not going to see a lot of problem solving around this. So this is a good point to stop this video. And then the next video lesson is going to be around problem solving using the first law of thermodynamics.